Hello. In this lecture, we'll talk about how Earth's atmosphere affects ground-based astronomical observations and why we put telescopes into space. Most of our astronomical observatories are on the ground, and although the atmosphere is great for breathing and all of that, it does pose a few problems for astronomers. The sky is bright during the day because of atmospheric scattering of the sun's light. The much dimmer light of most celestial objects gets drowned out, so astronomers can only work at night. And they can only work if it's clear. The sky is often filled with those pesky clouds. But even if it's night and spectacularly clear, there are additional effects that stymie the astronomer. Light pollution, atmospheric turbulence, and the fact that most forms of light can't even reach the ground. Just as our atmosphere scatters sunlight in the daytime, it also scatters city lights at night. We call this light pollution. Human-produced light pollution hinders our view of the stars, and it negatively affects astronomical research. But it's also an environmental problem. Light pollution disrupts ecosystems. It affects human circadian rhythms, and it wastes energy. It's estimated that approximately $2.2 billion per year is lost due to poor lighting just in the United States. And the problem of light pollution is only getting worse. If you're interested in the issue of light pollution and how to fix it, the International Dark Sky Association is a nonprofit that works to counter light pollution. Information on the IDA can be found at darksky.org. Atmospheric turbulence is another problem for the astronomer. Imagine a penny at the bottom of a very still pool. It's easy to see it, right? Now imagine someone does a cannonball into the pool. The image of the penny jumps around. Being on Earth under the atmosphere is sort of like being at the bottom of a pool. To do astronomy, we have to look through layers of air. The more still the air is, the easier it is to see the stars. The uneven heating and cooling of the atmosphere creates moving bundles or pockets of air. These air pockets act like little lenses. When the parallel light rays from a star hit the bundles, the rays bend in unpredictable ways. Therefore, when a telescope on the ground looks up at the night sky through the atmosphere, we get a twinkling and blurry image. Atmospheric turbulence tends to limit the angular resolution of ground-based telescopes to no better than about half an arcsecond, even if a telescope can theoretically achieve a smaller angular resolution. One technique to counter turbulence is called adaptive optics. Adaptive optics measures the atmospheric distortion and changes the shape of the telescope's mirrors to cancel it out. The shape of the mirror, often the secondary or another additional mirror, is changed slightly many times each second to compensate for the rapidly changing atmospheric distortion. A computer calculates the necessary changes by monitoring distortions in the image of a bright star near the object of interest. If there is no bright star nearby, a laser is used to create an artificial star to monitor for the distortions. This figure is showing a near-infrared image of a double star in false color. Without adaptive optics, the double star looks like a single star. When you're choosing the location of the next great Earth-based observatory, you want to minimize the effects of bad weather, light pollution, and turbulence as much as possible. The best observatory sites are dark, dry, calm, and high above the densest parts of the atmosphere. There are some sites around the world that meet these criteria. For example, the 4,300-meter summit of Mauna Kea in Hawaii. And in the southern hemisphere, the 2,600-meter high Paranal Observatory site in Chile. Of course, the best solution to our atmospheric troubles is to put our telescopes into space, where there is no daylight, no clouds, no light pollution, and no turbulence. This is why the Hubble Space Telescope, despite its modest mirror size of only 2.4 meters, has been so enormously successful. But there's another good reason to put telescopes outside of Earth's atmosphere. Earth's atmosphere poses a problem that no ground-based telescope can overcome. Our atmosphere blocks most forms of light. Astronomical phenomena emit light at all energies of the electromagnetic spectrum, so of course we want to look at everything. Only we can't, at least not from the ground. This figure shows the approximate depths to which different forms of light penetrate our atmosphere. Only radio waves, visible light, and the very longest wavelengths of ultraviolet light and small parts of the infrared spectrum can be observed from the ground. Therefore, the most important reason for putting telescopes into space is to allow us to observe the rest of the electromagnetic spectrum. The Hubble Space Telescope is probably the most famous space observatory, but there are many others that operate in parts of the electromagnetic spectrum that do not reach the ground. We'll talk all about these observatories in the next lecture. But before I leave you, I wanted to share this artist's work. Terry Cohen takes images from densely populated cities like New York, Rio de Janeiro, and Shanghai and removes the artificial urban lights. He puts the sky in as it would look if there were no light pollution. The images are lovely and haunting and best observed on your computer from a dark room. I hope you enjoy. I'll talk to you soon.